Okay, good morning, everyone. Couple of announcements. There will be a homework coming. I'll post it today, and it'll be due Sunday night, and then quiz on Mondays. In case I haven't posted it, but I believe I did mention it in the syllabus, right? Weekly quizzes. Typically, I have them every Monday. Okay, so that's like a regular schedule. First thing in the morning, Monday morning class, we'll be having a quiz every single week. So let's. Okay, so we stopped, I believe, right after, right here on this slide, right? We have the silicon lattice at at 0 K, 0 Kelvin. All the electrons are in place. They're occupying the slots in the covalent, and the atoms are arranged and binded together in a covalent bond. All the electrons are in place. The energy level for all is at the valence level, EV. Okay. As the temperature rises from 0 Kelvin, due to thermal energy, some of the electrons break free of their bonds and they're free to move around the crystal lattice, the semiconductor crystal lattice. And each of these electrons have charge, or they carry charge, and the movement of electrons is, of course, what we refer to as electric current. Every time an electron moves out of its spot, the atom, of course, is now an ion, but every time it moves out of its spot, it leaves behind an empty spot. That empty spot is referred to as a hole, and that hole is termed as a particle in its own right with positive charge. Okay, so when we look at devices made of semiconductors, we will treat holes and electrons both as particles. Electron particle with a negative charge and a hole with a positive charge, right? Now, the important thing to remember is that electrons are free to move around anywhere in the lattice, okay? Once they break the bond, right, they broke the bond, it can move anywhere in the lattice, does not have to occupy a certain spot. Holes, however, they are fixed. They can only move where the electron was present, right? So they are not free to move around everywhere. Make sense, right? Electrons are free to move around anywhere in the crystal lattice outside of the atom, but a hole, the positive charge, is always in a fixed spot. Okay. So now when the electron breaks a bond, and moves, this electron plus the hole that is left behind is termed as an electron hole pair. So electron hole pair. Let me scroll a little bit higher. So it's known as the electron hole pair, and the process is known as electron hole pair generation due to thermal energy. Okay. It is intrinsic to the semiconductor material. There is no external force applied on it. There is no voltage, no electric field, no radiation, no light, nothing, except for heat, thermal energy. Okay. Hence, it is also known as an intrinsic semiconductor. The carriers, so electrons and holes are known as charge carriers because they are moving around the semiconductor structure, so they're known as charge carriers. And intrinsic semiconductors, the charge carriers are intrinsic to the material. They're generated due to thermal energy, not due to any other external applied force. Okay. So I would say electrons and holes. Intrinsic to the material. and generation of this electron hole pair is thermal energy. No external source is applied. Okay, no external energy, no electric field, no voltages, no radiation, no light, nothing. So this is also known as a intrinsic semiconductor. So now the question is, how many electrons and how many holes are generated, right? We established that at 0 Kelvin, where it's so cold, there is no thermal energy present. Everything is at the valence level. As it heats up, let's say we are at room temperature. If we are at room temperature, how many electrons have broken free of their bonds? Okay, and that is described by the equation on the next slide. So first, let's actually no, let's go to the next slide. N represents the number of electrons. P represents the number of holes. In an intrinsic semiconductor, a hole is generated for every electron that breaks its bond. Okay, so by its very definition, N is equal to P. The number of electrons is equal to the number of holes. N and P, well, it just comes from negative and positive charges. Okay. All right, let's take a 5-second pause. Let me know if you have any questions. Any questions? Anyone?
Professor, I have a question.
Yes, go ahead.
You talk about P as in the number of holes, but I don't see P in the equation. So is that not directly related to the equation?
So the question being asked is, well, there is no P in the equation, so how is it not part of the equation? It's a good question and good observation, and that's coming, the explanation is coming right up.
Okay, thank you.
Uh-huh. Okay, so going back when researchers were trying to discover, you know, a suitable model and then write out equations for deriving these, they came up with the best that they came up with was the product of N and P. This product of N and P is Ni square. Okay, so here's where I used to be confused when I first started. N represents the number of electrons. Okay, but Ni square represents both N and P. It's the product of N and P. Okay, so in that sense, the Ni and N are not the same. Does that make sense? Right? The N represents the number of electrons, P represents the number of holes. And the equation that they derive, you'd have to take E524. And the equation that they derived was the product of n times p, that term to be, because it's n times n or p times p, right? So it's a square. N has to equal to p in an intrinsic semiconductor. So in an intrinsic semiconductor, n is always equal to p. So if you do n times n or p times p, you would get n square or p square. But they did the product of the electrons and the holes. They came up with an equation for ni square. Or you could also say n is equal to p is equal to square root of the equation that you see on the left. Okay. Bt cube e raised to minus eg over kt. Okay, so that's the equation. It contains both n, also it contains p. Once again, important to remember, in an intrinsic semiconductor, n is always equal to p. There would not be a hole without an electron breaking a covalent bond. So let's take a look at the equation. There's four terms: B, T, Eg, and K. Okay. All of these are constants except for temperature. Okay, everything is a constant. Eg is the semiconductor band gap energy. It's the band gap energy that is required to cross the forbidden gap. Right? For an electron to jump from the valence band to the conduction band, it needs to acquire energy Eg. That is a constant dependent on the material that you use. Okay. Then we have K, Boltzmann's constant. And then we have B, which is termed as a material dependent parameter. And it describes thermal conductivity of the lattice. It describes the mobility and the thermal conductivity of the lattice. That is also a constant. For silicon, B is equal to, let's see if I can't remember it, always 1.08 into 10 raised to minus, no, 10 raised to 31. 10 raised to 31, and the units are K raised to minus 3 and centimeter raised to minus 6. There was a new paper I was reading about some sort of different material, describes another factor in B. But in general, if you read any book, any article, they'll always refer to it as a material dependent parameter. Okay. Again, the answer for that would be in higher level classes. Okay, let's take a pause. Think over it. Let me know if you have any questions. Any questions? Okay. All right. So as I was saying, this equation describes the intrinsic carrier density, right? It tells us the number of atoms that are present in a semiconductor material. And T in Kelvin is the only variable. So there are a couple of examples in the book. I would recommend that you look over if they are solved examples. So please take a look. It'll take like less than 5 or 10 minutes. and try to solve it by using this equation. Okay, the answer is already available. So, and this is a standard equation, simple plug and solve. All right. So, solved example in the book. I'll mark it here. Okay. So this table here shows you a chart of the intrinsic carrier density as a function of temperature. Okay, and the band gap energy is also noted for the three most common semiconductors: silicon, germanium, and gallium arsenide. Now, talk about 2 or 3 parameters that are related to the intrinsic semiconductor. Okay, so we have intrinsic electrons, intrinsic holes that are generated in the semiconductor, and we state that they are free to move about the crystal structure. They are free to move about the semiconductor material. Now, if they're free to move about, what happens? Are they just randomly moving? Are they moving in response to the thermal energy? What happens if we apply an external source to it, okay, to this intrinsic semiconductor? And so the two terms that we are going to look at are drift current and then mobility, okay? So the equation for the drift current is given here. J is Q times V. J is actually the current density. Q is the charge density, and V is the velocity of charge, okay? Now, when intrinsic semiconductors are placed in a environment that is above 0 Kelvin, the electrons break free and they will actually move randomly. They will move randomly. If we apply an electric field to that piece of material, then the electrons and the holes will move in response to the electric field. And that movement is termed as drift. So if you apply an external electric field to an intrinsic semiconductor, the electrons will drift in response. And hence the term drift current. And of course, if the electrons are moving, then the holes are also moving correspondingly. And then this, of course, termed as drift current. That is one part of a semiconductor current, okay? There will be a second part, which is known as a diffusion current, but that comes after we introduce external impurities. And then the other point we talked about was mobility. So on the next slide, I'll wait. Okay. So then we have mobility. Now electrons and holes are moving through the semiconductor crystal. So we use a constant, a term to describe the mobility of these charge carriers, okay? Now, electrons are free to move about anywhere in that crystal lattice. Hence, their mobility is higher than the mobility of the holes, because holes can only move from a specific spot to another specific spot, okay? So if electrons are just moving randomly anywhere in the crystal lattice, holes can only move in localized spots. So Mu n and mu p describe the mobility for electrons and holes respectively, and these are known as the proportionality constants or constant of proportionality. Okay, constant of proportionality, where E is, of course, the applied electric field. Applied electric field. So loosely, generally defined or loosely defined, mobility is basically how fast or how slow the charge carriers are moving through a semiconductor material. Mu n is 1420 and mu p is 470. The electron mobility is a lot higher than hole mobility. Yes. Yes. So it's centimeters square per volt times s times second. Which is also here, left. Yes. I'm talking about, oh, the magnetic permittivity. Yes and no. No. Sometimes we use the same symbol for a lot of different things. So the question being asked is, why are mu and mu p different? The answer is because electrons are free to move around anywhere, and holes can only move from localized spots. Holes cannot move, or first of all, holes are not generated until the electron actually moves somewhere, right? So that electron, let's say just one electron that has jumped free. Now the hole is just in one spot, but the electron is moving around already. It can move around anywhere within that crystal lattice. If there are no further openings, that hole is just there, zero, right? It's not moving anywhere. Any questions? Okay. So the next question would be, if you want higher speed devices, then you can apply huge electric fields, right? And you can create higher speed devices all the time. But that's not the case. We're all governed by laws of nature, laws of physics, and there's an upper limit on how high an electric field we can apply before we approach diminishing returns. And so basically your speed could be linear for a while, but then it approaches the limits and it saturates. Okay, and it saturates. And that phenomenon is known as velocity saturation. Okay, so this chart here shows you the carrier drift velocity versus applied electric field. Okay, and you can see here around 4 or 5,000 volts, it starts to saturate for all three semiconductors, silicon, germanium, and gallium arsenide. So for silicon, typically upper limit is generally taken as 5,000 volts centimeter. So that's it. It's when you're working with a micron scale, that's a huge amount, right? 1 centimeter is 1 over 10,000, 10 raised to minus 4. I mean, sorry, the reverse. 1 micron is 10 raised to minus 4 centimeters, right? 10,000 microns is equal to 1 centimeter. So that's a huge number. So even though we may be working with digital electronics, which is like 3.3 volts or 5 volts, because it's a micron scale, it's the electric field is huge. Okay, and so that places an upper limit on how fast you can operate your devices. Okay, so for high frequency or high speed devices, we use alternative semiconductors. Silicon is not always the best choice when it comes to high frequency applications. For that reason. Okay, so that was intrinsic semiconductor. Now we come to the actual creation of the foundation of how and why we can use these devices. So, and yeah, it's literally known as doping, semiconductor doping. So semiconductors by itself, as we said, they have some free charge carriers at room temperature, but they are not sufficient enough to be classified as a conductor. What makes it a conductor is if we add external material into our semiconductor material. So let's refer to just silicon, right? If we just refer to silicon for the purposes of the next few slides, silicon has 4 electrons in its outermost orbit. Some electrons might have broken free of their bonds, so they're free for conduction. But again, we cannot control that process. Yes, we could apply an electric field and we could have some sort of current, very low amount of current flowing through it. But the magic happens when we add external material. That external material comes from column 3 and column 5 of the periodic table. Typically for silicon, it is boron and phosphorus. Okay, typically it's boron and phosphorus from column 3 and column 5. Okay, now column 3 element has 3 electrons, column 5 element has 5 electrons. And so we can then convert our intrinsic semiconductor into an actual conductor. And because we can choose how many atoms we introduce into our material, we can control the operation of those devices. Okay, and that's the key thing. We control by choosing the dosage of this material. Okay, by choosing the dosage of the external material. This external material is referred to as the dopant. It's dope. And because it is an external material, it is also referred to as an impurity. But the important point is that everything is controlled. Okay, everything is controlled. And that allows us to create devices that you can build circuits. Yes. Not melting. There's a process called diffusion, and there's another process called ion implantation. So in diffusion, we spread the material on top. It's like spreading butter on bread, and then we stick it in a toaster, except the toaster is 1,000 degrees C. And so then material just diffuses inside. So yes, that kind of, we can say it's an alloy junction. But that, again, EE 424, clean room class. So column 3 and column 5 materials are introduced in there. What happens when we introduce a column 5 material? If we introduce a column 5 material that has an extra electron, 4 of those 5 electrons will bond with the neighboring silicon atoms. And then 1 electron is left free. So without doing anything else, you now have an extra electron for every atom that was introduced in that silicon crystal. Make sense? Intrinsic semiconductor, electrons break free of their bonds. A doped semiconductor, you're introduce an external atom into the silicon lattice. Because it has an extra electron compared to the silicon atom, that electron is free to move about the semiconductor lattice. Okay, so column 5 elements, 1 extra electron, and this extra electron is free to move about anywhere in the semiconductor lattice. It's important to remember there are no holes corresponding to these electrons. Okay, no holes are created. The positive charge corresponding to this electron is bound in the nuclei of the introduced atoms. Okay, so those positive charges are within the atom. So let me draw it better. Okay. Oh, that, by the way, is a phosphorus atom. Should have. Okay, column 5. No holes are created. The charge, however, is exactly the same. Right? If you introduce 1 atom of phosphorus in that silicon lattice, 1 extra electron is created that is moving around, extra negative charge, but the positive charge corresponding to that electron is still present in that atom. So it is not free to move about. So now you have an excess of electrons and free negative charge carriers. Free in the sense they're free to move about. Free negative charge carriers. And because it has an excess of N, this material is also known as N-type semiconductor. N-type semiconductor. And because it donates the electron to the intrinsic semiconductor, it is known as a donor impurity from column 5. from column 5. Let's take a 10-second pause. Think over it. Let me know if you have any questions. Probably longer pause, actually. This is actually the most important concept of how semiconductors are created. Yes.
Or basically just trying to get rid of the holes then by adding in new elements.
So the question being asked is, are we getting rid of the holes? No. The holes that are present due to the intrinsic conditions, they are there. They are present in the semiconductor. We are just introducing more negative charges in our material. Hold on. Yes.
So now if you add heat to this, what happens? Does the electron is already free and it jumps into the open loop?
That's a good question. So the question being asked is, if we increase the temperature, what happens? Yes, more carriers are generated, and we will actually see this in lab 1. Well, not lab 1, experiment 1 of the lab. We'll do a simulation where the temperature of a diode increases, and you will see a corresponding drop in the voltage that is required. So there is more charge carriers available for conduction, so it's easy to create a current flow through that device. Yes.
Why? It seems like you're reducing the control of the semiconductor. That actually allows the path.
So the question being asked is, if we introduce more impurities we are introducing impurities into our material, aren't we losing control? The answer again would be no, that because we are controlling how many atoms are being introduced, and we are controlling where exactly they are going. So the way when we make these devices, it's 2D structure. And so we have our silicon wafer that is, and I'm showing you the top view. Let's say this is a silicon wafer. We have a specific number of atoms and dosage that we are introducing in there. And we mask the spots where we want or where we don't want our atoms to go in. And so we use special materials, and we create what is known as a mask. And so the answer is no, we don't lose control. Open space for the atoms to actually go through into the silicon material. So this is the top view. And this just shows like a simple plus sign, right? That's the thing that came in my head. But if you're creating a diode or a transistor, or let's say you're laying down a wire, for instance, if you're laying down a wire and you want a connection to run from, let's say, point A to point B, and then from point C to point D, that's how you would do it. Because the more impurities that are present, the more we are pushing our semiconductor to become a conductor, right? The whole point is to control the amount of current that's flowing through. So the more impurities we implant in there, the more we are controlling and more we are trying to make it into a conductor. And then we can, of course, control the device behavior using external electric fields. And so let's see, what was I saying? Open space. Okay, open space. So there are quite a few steps involved in there, and I'll talk about those on Monday. I'm going to bring a few silicon wafers into the class. Let's see what else. Oh, a doped semiconductor is charge neutral. Okay, it is charge neutral. The reason, of course, is when you have intrinsic carriers, intrinsic charge carriers, electrons break free, electrons and holes are the exact same number, no difference. And then when you introduce external impurities in there are extra electrons, but each atom has the same number of positive and negative charges. It only happens that the electrons are free to move about and the positive charges are not. Okay, so the holes that are present in there are due to the intrinsic hole generation. Electrons are due to the intrinsic hole generation as well as the external donor impurity. Okay, so two of them. And the same thing happens when we introduce a column 3 compound in there. Not compound, sorry, column 3 material. Okay, column 3 would be boron, has 3 electrons in this outermost orbit. Because it has 3 of them will bond, 3 of them will bond with 3 silicon atoms, and 1 bond will be left open. 1 bond will be left open, thus creating an empty spot. Right? It creates an empty spot in there. And that empty spot is a hole. And then other electrons are free to jump into that empty spot, thus creating more holes throughout the crystal lattice or throughout wherever we have implanted our impurities. Okay, so this is column 3. Example here is boron. It's another example of where we use the letter B for boron as well as for that material dependent parameter. It's also used in the inductor equation, magnetic flux lines. It's also used as a unit. Anyway, column 3 compound, column 3 atom like boron has 3 electrons in the outermost orbit, and it bonds and creates a hole opening. So these impurities are referred to as acceptor impurities or acceptor dopants. Okay, it creates an excess of positive charges. Excess of holes, and hence it is also referred to as a p-type semiconductor. A p-type semiconductor. Okay, so column 5 compounds create an n-type semiconductor. Column 3 create a p-type semiconductor. It has an excess of positive charges versus a n-type semiconductor that has an excess of negative charges. And once again, the holes that are present in there are due to both intrinsic as well as the extrinsic dopant. But the electrons that are present in there are solely due to the intrinsic environment. Okay. So there's an excess of holes, and hence it's a p-type semiconductor. We typically, when we buy silicon wafers, there's already background dopants in there. We call it the background concentration. Meaning when we buy a silicon wafer, we might buy usually N-type silicon wafers. So it's already doped with phosphorus throughout the entire wafer. It's kind of like uniform. There are some variations, of course, but it's like uniform. And then when we take the wafers in the clean room, we might implant boron in there. We open up tiny holes in the silicon material, and we implant boron in there. So now we have a p-type and an n-type in the same semiconductor. And that's how we would create semiconductor devices. So charge carrier concentrations, well, electrons and holes are referred to as charge carriers. They are the ones carrying charge. If a semiconductor material has both N and P type impurities, we look at the number of holes and the number of electrons. If the number of electrons is larger than the number of holes, it's an N-type material. If holes are larger, it's a P-type material. Now, because there are holes and electrons both present in the same material, and the number is not equal, okay, number is unequal, we refer to the charge carriers as majority and minority. So in an N-type material, electrons are the majority. So in an N-type material, electrons are referred to as the majority carriers and holes are referred to as the minority carriers. Okay. So N-type material, electrons, actually, let me just use N. N are majority carriers and P are minority carriers. And then the same thing in a P-type material. If it's a P-type material, then N are minority carriers and holes or P are majority carriers. Okay. Let's see, last couple of minutes. ND and Na are basically the concentration of the atoms. Okay. Nd and Na are the concentration of the atoms that are introduced. So they are referred to as atoms per centimeter cube, 1 cubic centimeter of volume. So how many atoms we introduce into that volume? Okay. All right. A few seconds left. Let me know if you have any questions. Yes. Any questions? Okay, so we'll end class here today, and we'll see you all on Monday, bright and early at 8 o'clock for a quiz. I will post everything on there, but in general, every Monday, the quiz will always be on the material that is covered in the past week. Okay, so everything we covered on Monday, Wednesday, and today, Friday, will be assessed on Monday. And this time, I'm most likely have like a few short answer questions based on the theory, the concepts, maybe short problems based on the equations. But other than that, it should be rather straightforward. Okay, so review the material, the lecture videos, read the textbook. I know reading is kind of a lost art now, but definitely read. And then let me know if you have any questions. Yes. Same, chapter 2. Chapter 2. Even the topics and the corresponding. So I kept the names also kind of the same so that students, can find it easily.